Okay, let's start it. Yeah, I saw the one question comes in Piazza, but yeah, it's a 2 last minutes, so I don't have a times to answer, and it's a bit unclear what was the question. So if you have that question, if you are the someone who made that question, just come to me in the office hour. Okay, yesterday, last in the last lecture, I remind the final final project, but we didn't talk about midterm actually. This one is coming earlier than the final project. The midterm is 2 weeks from today. So including today's lecture, we have a 3 lecture remained before the midterm. There is no surprisingly difficult problem going to be in the midterm, but you can have one cheat sheet, size US letter size, both side is feel free to put whatever you don't want to memorize, but can be useful. Problem is going to be similar to the practice question level. It's going to mostly about the kinematics, maybe one simple dynamic problems, depending on the how we can make a progress until next week. The week we have a exam, we're not going to have a lecture on Monday. It's a holiday. So that's why we have a 3 lecture, including today's lecture. Any other question? Oh, this is important. If you need any additional accommodation, please send me the email as soon as possible. I need to coordinate other things according to that, accommodation request. Is that okay? Question? It should be different. Is it same? Oh yeah, TA is a mistake. Good catch. Thank you.
I think the Monday of the Indigenous Peoples Day, no class, but the Tuesday is Monday's schedule, I think.
Oh yeah, we're not going to. Because we have enough lectures. Good thing, right? Let's move on. So I know last lecture is about the Adjoint map, which is basically where we can use to calculate the Jacobian. And see there's some confusion. So I decided to spend one more lecture for kinematics. So going to show the step-by-step explanation how we end up with this formula. And don't forget the end of our goal is to calculating inverse kinematics, to find the inverse kinematics. And that's why we need a Jacobian. And the Jacobian is basically velocity mapping. So that's why I keep talking about the velocity. Okay, let's put this system down to the planar plane. So let's think about only 2D movement. One trivial question is that what is the angular velocity of this point when there is a rotation and linear motion at this point? The answer is pretty simple. It's the same, right? Angular velocity is the same. Actually, angular velocity in whatever origin you pick, angular velocity is going to be same. It's a rigid body rotation is shared by everyone, so every place. Linear velocity, by the way, are different, right? If you're far from the rotation axis, you're gonna see more linear velocity. And the formula is simply omega times L. L is momentum. So if the momentum is longer and longer, you're going to see the larger and larger velocity because of the rotation. And if it is zero, you're not going to see any linear velocity because of rotation. But here, the things you should not forget is that there is still some linear velocity. So then you have to include that linear velocity. So far, so good, right? Uh, and we also know that the linear velocity and actually angular velocity as well is not, consistent to every place. What it means that as you change the frame, the x directional velocity can be seen as the y directional velocity. It depends on how you define your x-axis and y-axis. So that's a frame transformation. And we have a nice way to concisely represent this frame difference, which is rotation matrix, right? So if we want to read the angular velocity described in the frame 1 in the frame 2, then what we need to do is just multiply the orientation matrix describing the frame 1's orientation from the frame 2's orientation, which is R2 to 1, multiply to the angular velocity and multiply to the linear velocity. And this linear velocity is omega times L, right? So there is no confusion in the planar case. So we're going to do the exactly same things, but this time we need to use a cross product. And this cross product, following the right-hand rule, align your finger to the first vector and grab it to the second vector. Then thumb is pointing the resultant vector, omega cross product P, is give us the linear velocity direction and adding up the linear velocity and do the rotation. That's it, right? That's all we have to do. And question?
The rotation matrix is from frame 2 to frame 1.
Yes.
So kind of thinking of what it means to apply it to the angular velocity.
So angular velocity in this problem setup existed in the frame 1, frame 1's origin. And then because of that angular velocity, you're gonna see the linear velocity in everywhere, right? If I wanna know that what is the linear velocity at the origin of frame 2, then you have to multiply, actually cross product, this angular velocity and the distance between the frame 1's origin to the frame 2's origin. Does that make sense? What is your confusion? Okay. Anyone who need more explanation about this one, the linear velocity part? So one more things, cross product. You can calculate the cross product by switching this omega to skew symmetry matrix form. So far, so good, right? That's actually almost all things we learned last lecture. So now we can do this. Okay, you can do this, right? Exercise. Okay, is that problem clear? The first one is angular. First three is angular velocity. Second three is linear velocity. And this don't be confused. This transformation is from A to B, not B to A. You have to flip if you wanna use this to transformation from the B to A.
That origin of frame B with the frame A. Origin of frame C with the frame A.
No, when its origin is 0.5 to the y direction 0.5. Question?
I just simply like, is it because like I'm trying to change on basis, like changing the basis vectors. So like so originally I rotate from one to zero, and now I'm going to represent this vector that's in the basis of this the coordinates. I will apply like its inverse. I want to like if this is equal to like string blank to transpose.
Oh, yeah, the same. Yeah, 1 to 2 transpose is same as R.
Yeah. So if I apply like 1 to 2 transpose, I mean like it's kind of like I want to represent this new vector in this coordinate system.
No, exactly. So you're not reading the vector. You're actually calculating the velocity caused by this rotation. So it's not just need the same vector in two different ways. You're actually influenced by the rotation of this. Does that make sense? So if you see the omega and g described in the frame 1, but in the frame 2, then you just multiply R2 to 1 and around R2 to 1 plus 3. You don't need the rest of the
So in the global frame, your angular velocity is stable, and the linear velocity is this one plus yeah, I mean, if your linear velocity is stable, right, velocity introduced by this angular. So I'm multiplying this linear velocity and representing the frame.
Yeah, here you these are two people that we were describing that vector in the frame 1.
So this matrix is kind of like representing
Because it says like a velocity.
You see that vector in different data vector in the frame 1 because this omega and v are both describing the frame 1, which I didn't put in other file. Yeah, so omega is currently y.
I need to describe it. Okay, so that makes sense. Thank you. So here. Yes. Yeah, sure.
I don't know what.
Yes, yes.
Yeah. Maybe because it's all. Oh, yeah. I'm creating insurance that are going to watch Parliament.
It's from frame A to frame B.
For the angle of together. So any of them,
It's the same matrix, you don't have to get the.
You need B to it. Because I answered, we need, we need peace.
I see. This should be. And the velocity of the origin.
Yeah, you can.
Origin, original frame, the original.
Now you can apply just on zero. So it's a part of two. Don't use troops though. Oh, why? Sure.
It's very like this. And the angular velocity remains going forward. Going to receive it from the max of the equations. So we need
Include the cross product.
I wonder.
Basically, we're gonna find the aspect of the one frame right now.
Yes, secondary, but in the.
I forget that, I mean, I was trying to remember how to explain.
You need to put it like. Yes, it is. So X one is X one is zero. One here.
Yeah. Or, yeah.
Yeah. And zero.
Yeah.
No, X one is X one minus this. And then you still it's just zero. I think this is zero and this is.
What's this thing? So it's like you do that.
Wait.
So what's the X? Minus X, Y minus Z.
Okay, yeah, yeah.
So this is times with this one. And
No, wait. I meant that, yeah.
it's just calculate this way to calculate this. And what's in sit? R. Oh, yeah.
This is X one.
Yes.
Minus X one. X cubed.
Yes.
Minus X.
It's the same. This is gonna be
R and. Yeah.
zero. Oh, two, R2, 1. It's just right. Yeah, basically.
This looks like zero.
Yeah.
This looks like.
You to multiply by.
Something's wrong with my calculation.
So this is zero.
No, this is zero.
And plus zero is zero.
Oh, so this is just zero.
And then this is one because plus one.
Yeah, but I'm saying that,
The first one, right?
Yeah.
Just getting lost around my head. Oh.
how can you get a Q back from cross from number 0, 0, 0? How is it possible to? But it's the cross.
I'm sure it's one.
This one? So you got 1 over 2. The z, just 0 minus 1.
Is symmetric.
Oh, it's. This is minus d. Oh,
But if you transpose it, it's
no, we can transpose the rotation matrix.
Okay,
Not the-
skew symmetry is.
So this looks like a symmetric matrix. Well, this looks like a symmetric matrix.
Yeah, then you made another mistake.
The mistakes here, yeah, yeah. Okay, excellent. But that doesn't make any difference.
Yeah.
Oh, yeah, it's.
All right, I think
Wait, like that.
I think we are ready to move on. Maybe? Can I?
No, it doesn't,
Okay, let's solve this together. I think many of you already got the answer, but let's do this together. So angular velocity part is relatively simple. We have angular velocity described in the frame A, which is 0, -1, 1, right? So what we need to do is just describe the same angular velocity in the frame B. And currently we have RA to be 1 over square root 2 minus 1 over square root 2 square root 2 0, 0, 1, 0, 0. By the way, can you recognize what this orientation means? What is the rotation? What is this rotation? Yeah, 45-degree rotation around the z-axis, right? Is it plus 45 or minus 45?
Minus 45.
Yeah, great, everyone. Now you can read this 3x3 matrix. Well, proud of you. So here we need B to A. So we need to take a transpose of this. And multiply with -1, 1. Here we got 1 over square root 2 and -1 over square root 2. Uh, 1. That question?
Could you please repeat one more time why B to A difference between the two that you have here?
So let's visualize this. This is frame A, and currently angular velocity pointing -y and z. So probably pointing in this way, right? And the B frame rotating around the z, but -45 degree. So it must be something like this, right? Looks occurred. Trace. Right. So I want to describe this vector in this frame. That's the goal. So then I need orientation pointing frame A from the frame B. So that's why I need rotation matrix from B to A, not the A to B. Does that make sense? Question?
That's so one over root two negative one over two one is the angular velocity of B, right? Like,
This one?
yeah,
Yes.
okay.
By the way, angular velocity is shared by everyone. Just describe it in a different frame. Okay, linear velocity is, to calculate the linear velocity, we need omega cross product P things, right? And here is the P. What we need is this one. And then we're gonna take the omega cross product of P first to get the linear velocity of the frame B because of the angular velocity. So then omega is x is 0, y is -1, g is 1. So cross product form is this, right? And it's gonna multiply with a p, which is so it's -1, 0, 0. Right? Did I make any mistake? And this frame A is also has a linear velocity, which is 1 to the g direction. So this velocity of the frame P is -1, 0, 1, -1, 0, -1, 0, 1, -1, 1. Yeah, something like this, right? This B is -1, 0, 1. But this velocity currently described in the frame A. So we need to multiply this with this one again. Then at the end, it become a the P described in the frame P is -1 square root 2 -1 square root 2 and 1. Right? Is that all consist question?
About the notation, so is the bottom left the point and the bottom right is the frame for like vectors?
Bottom left is frame, bottom right is velocity of name of this velocity.
Yeah.
Okay. Did I make any mistake? Why your face so suspicious? Okay. Even in the case my math is wrong, you got the point, right? Okay, let's move on. And if you okay. Now we can just describe everything in a single concise representation. What we've done is basically R times omega and R times omega cross product P plus R times V1, right? So we can do the same things for the second frame as well. So following joint and just add up this velocity, spatial velocity, give us the end effector velocity. And here, don't forget, this orientation matrix actually multiply in the omega cross product P, not omega, and then cross product. And you probably already noticed that this is a bit different from the equation I showed in the last lecture. Previously, it was P cross product R, isn't it? Not the R cross product P. Do you remember that? Okay, let's move on. So there is one more thing I want to also mention. This is something I mentioned multiple times, but the vector we're currently thinking about is pointing our target frame from the origin. And this vector can be described in two different places. One is the frame 1 or frame 3. So actually you can pick any frame, then you can describe the same vector in a different way. At the end, you're gonna get the 3 number, which is vector form. So it can be all different, but representing the same vector. So that's the coordinate idea. It's not about you changing the vector, you just see the vector in a various place. Okay, you got that point, right? So now I'm going to change this R times omega cross product P to the P cross product R, which is equation we got the last time. Here we are. And if we want to do if I change the cross product to skew symmetry form, then it's going to be something like this, right? And even I add up the R 1 to 3, 1 to 1, from 1 to 3, and the 3 to 1, because these two are going to cancel out. It's okay to add in between these two, right? So far, so good. And I make a transpose of this. And then I can put this inside of the skew symmetry form. No need to memorize this. But anyway, this is formula. This is also another way to describe the adjoint, but just I'm going to explain only 6x6 matrix form. There is another way to apply the adjoint mapping, but anyway, this is one way to putting the rotation matrix inside of the skew symmetry matrix. So we can do this. And then we can also flip the cross product part like this. Cross product times R omega. And here what we done is just cross product flipping. So A to B versus B to A is the same, but with a different sign, right? So we are almost there. And we just flip the sign, because so far this vector pointing from the A1 to 3, but we need 3 to 1. Then we end up with a P cross product form times R times angular velocity, which is going to make our adjoint mapping is nice and concise. And at the end, our adjoint mapping 6x6 matrix going to be this. We call this adjoint. Ta-da! You didn't realize that I just skipped through this P cross product part, right? One student's actually asking me why this is P cross product R. Because I keep saying omega cross product P give us a linear velocity, right? P cross product omega. Okay, anyway, this all the term we can see here can be extracted from the transformation matrix representing frame change from the 3 to 1. That's why we spend this much effort to switch the P. Just previously it was 1 to 3, right? We changed the 1 to 3 to 3 to 1, and then also flip the frame representation, because we don't want to do anything except just plug in this number to this adjoint map. So far, so good. Well, now we are in here, almost there. So Jacobian, we can use this equation to build up the Jacobian, because angular velocity and linear velocity caused by two different joints is just the summation of it. So it's represented in this formula. And S1 is axis times angular velocity. S2 is also axis times angular velocity, the second joint velocity. And I also showed the example of this S1 and S2 in the previous lecture, right? This S1 and S2 is actually really simple. In case of this one, S1, which is first joint axis, is nothing but 0, 0, 1, 0, 0, 0. Okay, then we can make these things in matrix form by picking up this theta1 and theta2 dot. Then this is exactly the Jacobian form, right? So we can use this for Jacobian calculation. Done, right? So we can now solve this last in-class exercise we stopped in the last lecture. So this is not in-class exercise, so I'm going to just do this together. Do this with you. Let's put the other joint formula somewhere in whiteboard. Why this is so hard? And the factor Jacobian of this 3-degree freedom manipulator is going to be 3 by 3 matrix. Am I right? No, 6 by 3 matrix, right? Am I right? 6 by 3 matrix. Because we need and the effector velocity, angular and linear. So anyway, anytime when I ask that the full Jacobian, then number of law should be 6. First 3 is angular, the last 3 is linear. And the column is going to be determined by number of joint. So anti-effector Jacobian is going to be 6 by 3 matrix. And I'm asking only the last column. And this last column is adjoint T E to 3 and S3. And the S3 is, what is S3? 100. Great. And this T EE3 is okay, let's start from the orientation. Orientation is identity. Does that make sense? And the position, great. Can you just try to write directly here? Okay, we can do the adjoint. We can build up the adjoint map like this. I 0 P cross product form, which is 0.100000 minus 0.100, and R is the identity, so we don't need to put it. And plug in that 1000000, and we know this is ends up with just 100 and 000, right? So it's going to be same. One way to interpreting this vector is something like this. So as I explained previously, if we fix this elbow and this wrist joint, then this is exactly same as this robot, right? First, yaw, second, pitch, and third one is a roll. So this vector, first 1, 2, 3, asking that if this third joint rotates, then what's the angular velocity we're gonna see in the end effector? So then we know that it is only possible to make roll directional velocity, right? And this fact, the x directional velocity going to be made, and y and z is going to be stationary. is true, even though there is the other joint movement, right? So it's independent from the joint. So that's why we don't need to worry about any theta component, theta 1, 2, 3 component when you decide at the third column of this Jacobian. And this is linear velocity. And the linear velocity is also kind of this thing. If we have some number here, which is going to be multiplied by theta 3, what it means that because of this rotation, this end effector can go forward, which is impossible, right? It's only possible when you are in this posture. The end effector can move forward and backward when you have an extra degree of freedom or prismatic joint. But this simple x-axis rotation cannot make this end effector moving forward, left, or up. So that's why all three numbers are all 0. So we can actually do, at least the certain things intuitively by just imagining what's going to be because of this rotation. Okay, of course, this vector and this vector is function of the theta. So it's not trivial to find because once we calculating this adjoint map, then we need to use T E to 3, and this is function of the theta 3, right? So we need to put the angular rotation matrix, and probably the T can be also a function of the theta 3. And this E to 2 is actually theta 3 and theta. No, this 2. And this is 1. And theta 3 and theta 1 are theta 2. So it's more than intuition. But at least in this posture, we can just describe we can just think about what's the Jacobian. Let's do this together. For the second column, yeah, we already know this is 1, 0, 0, and 0, 0, 0. For the second column, we want to know that what's the angular velocity caused by this motion, right? At this 0 posture. I mean, if it is this, and if it is this, if it is this, then it's a bit confusing because, I mean, if the roll is 90 degree, then same movement, making the x directional movement instead of the g directional movement. But in this posture, at this posture, the rotation, rotation around second joint, making only y directional angular velocity, right? So this should be, right? How about linear component? Once it rotating this way, then instantaneously you're gonna see down velocity, right? Is there any other x or y directional velocity? No, right? No, right? There is no x or y directional velocity at this posture. So then, 0, 0, and this number is 0.2 minus. Does that make sense? So if the 1 radian per second velocity made in the second joint, then you're gonna see the 0.2 meter per second downward velocity. Question? So because this link length is 0.2 in this diagram, when this joint making the 1 radian per second angular velocity at this posture, then you're gonna see the 0.2 meter per second downward velocity at the end effector, right? That's why we're gonna get minus 0.2 here. Oh, great.
Why is there no velocity like this direction?
X direction
Yeah, because it's, I feel like it's going.
down, right? Yeah, that's a great point. It looks like an end effector moving backward as well, right? But at this posture, after one, picoseconds, there is no movement to the X direction. At this posture, it happens after this point. This point, actually making downward velocity and the backward velocity at the same time. But in this posture, you cannot. Do you understand what I mean? Yeah. So once the posture is changing like this, you're gonna see the some X component here as well, which is 0.2 times cosine theta. I mean, actually sine theta. But at this posture, you cannot. Good point. Right? No. Okay. First column, angular part. Someone said speak up. Yeah, great. 0, 0, 1. So one good thing is that now you can see angular part is all filled with identity. So even with these three joints, you can make a x, y, z directional velocity, angular velocity in, as much as you want with the joints. This is a two leg, at least in this position. How about linear?
0.20.
0, 0.2, 0. Great. Good. Any additional explanation do you need? Makes sense, right? To the y direction. Okay, that's it. That's the Jacobian. Now the next part is relatively simple. Inverse kinematics. Once we have a Jacobian, then inverse kinematics is, yeah, just more apply the Newton lesson. We already seen this graphics again, right? So putting this, and this, and we can, pick the numbers once the error is small enough. Once we are happy. Well, so far, difficult part was this one, Jacobian inverse, because calculating Jacobian is a bit tricky, but error is kind of okay, right? Really okay. How do you calculate the error?
What is the dimension of the Jacobian?
Here is a 6 by n. N is number of joint.
And the dimension of the Jacobian is the same.
So in this case, it's 6-degree freedom, so it's same. What do you mean the inverse of?
The pseudo inverse.
Pseudo inverse of the Jacobian. Different, right?
It should be 3 by 6.
3 by 6. Yeah. Because it's this part, pseudo inverse, going to multiply with error, which is 6 dimension, and updating Q, which is 3 degree of freedom. No worry, because your homework going to have a 6 degree of freedom robot arm, so it's square matrix. Nice 6 by 6 matrix. The question is how to calculate the error, right? So we do the Jacobian. Now what we need to do is calculate the error, multiply with the Jacobian inverse, getting the updated point position, right? So the question is how to calculate the error. And we already know how to calculate the error, right? In case of the rotation, we just transpose times this, right? Goal transpose times end effector current orientation give you the error. Am I right? Maybe I'm right. In case of the position, it's simple. Just subtract one from the other, right? Desired target minus current. Describing the which frame. So now you have to think about how you gonna define the error. Because you can define the error error in a many different way. One is the orientation. You can describe the error in a two different way, right? Implicit way and explicit way. Do you remember what is the implicit or which one is question? Okay. Yes, you're right. Great. Which one is local, by the way? I'm glad that you don't forget. You didn't forget about that. Yeah. If you define the error in a local frame, that is the implicit matrix form, and that's the how it works. So define the error in the local frame has this meaning. You're here, your end effector in this orientation. Okay, let's use a nice one. This orientation, and by adding up the error, you're gonna go to goal. And by adding the error, actually determine the how you describe the error. If it is the integrate multiply behind the current orientation, that means that I'm gonna define the error in the local frame. So then error definition going to be this, R transpose R. If I define the error in the local global frame, then what it means that it's going to be something like this. So error is defined by R goal times R and the effector transpose. Okay, then you're gonna get 3x3 matrix, right? Still need to transform this 3-dimensional vector to multiply with the Jacobian. The Jacobian is not designed to multiply together with the orientation matrix. And that part is something we already know. We know how to transform this to small SO3, which is vector form, and apply this equation, then we're gonna get error. So that's the angular orientation error we're gonna use. Okay, then we need to use the proper Jacobian, right? So far, this Jacobian describing the angular and linear velocity because of the joint velocity describing in the local frame, right? So to use this Jacobian as your Jacobian, you have to define your error in the local frame. So if you define the error in the global frame, you have to use Jacobian defined in the global frame. Does that make sense? So this is just Jacobian form. You should calculate this. And how to transform the Jacobian, we say it's a body Jacobian, to spatial Jacobian, global Jacobian. You just putting the pure rotation of the joint. What it means that there is no transformation, just rotating this frame in the global frame. That's what world Jacobian definition. And here, pure rotation of joint is nothing but just this one, rotation matrix and rotation matrix. Once you're putting something here, then it making, angular velocity times cross product with a linear position. So this one, this other joint is just see the same frame without anything, just see in a different perspective. Because your linear velocity x, y, and z is defined in this direction, right? But if you define the error g in this way, then you have to use this Jacobian. Jacobian defined in the global frame. So that's why it need rotation, word to end effector. Question? And orientation. Yeah. At the point when you calculate the inverse kinematics, you actually have all the information. You need every information, every link, orientation and position, joint position, and the end effectors orientation and position. Because your end effector, target end effector position and orientation highly likely defined in the global frame, right? you want to move the arm from point A to B. Normally, this point A and B is not determined by relatively defined in the end effector. Normally defined in the global frame. This is just animation if you made a mistake. So let's say this is our target point, target frame, orientation and position. And currently, robot, this is also 6-degree freedom robot. Here, if we use the proper Jacobian and the error definition, then it goes to target right away. If you mix this together, so you define the error in the global frame, I mean here, global frame, but using the body Jacobian, then you are going to see couldn't go to, because you're saying that your error is 0.2 and then move to the vertical direction, but actually you have to move to the left, right? That kind of things can happen. Surprisingly, if you just continuously wait with a very proper step size, then even this one actually converge. Because around the solution, the gap between the two different Jacobian is pretty small. But don't be fooled by that kind of artifact. Just make sure that you're using the consistent definition in both error and the Jacobian. This is U-turn loss and inverse kinematics forward. And that's it. Any question? Yeah, until you actually writing the code might be hard to accept, but as you try the different thing, it's going to be more clear. Any question? By the way, this is our last kinematics course, kinematics lecture. In the next time, we're gonna study dynamics. Question? Inverse kinematics? Yeah, not that I know. As far as I know, I mean, Newton-Raphson is not specifically about this algorithm, right? It is about the gradient and error and the continuously reduce. So other than using reinforcement learning, for instance, then there is not much variation you can make because it's already very general, Question?
No problem. Algorithm.
What do you mean?
I thought it's like a more efficient application algorithm, but it's only used for, I only see it used for optimizing.
You're talking about another optimization. Yeah, because this is gradient and error. So basically what any kind of the optimization algorithm should serve inverse kinematics, because the goal is minimizing the error. By the way, you can do it as your final project if you come up with a better inverse kinematics algorithm. Okay, that's it. Have a nice weekend and see you on Monday. Okay.
So this represents this represents the rotation around the first column, right?
Wait a second.